speaker for the day is Aditi Ahuja, who will be speaking on a peek into profiling custom and otherwise. Aditi Ahuja is a software developer who loves venturing into newer and niche fields in this subject. Please welcome Aditi as she'll be giving the speech and a talk on this. Thank you.
Good afternoon. My talk is titled A Peek into Profiling and presents a view of profiling focused on the internals. So, a bit about me. I'm a software engineer at Couchbase and I have spoken at Prometheus Day EU earlier this year. I am a gopher if that needed any mentioning here. You can connect with me using these handles. So, a brief agenda for this talk. This is primarily my exploration of the internals of the Go profiling tool pprof, straight from the source. I start by talking about pprof from the point of view of a user, and in the latter half, I go into the internals. So just quickly, profiling is used to glean insights into code performance and bottlenecks. And the choice of weapon for this in the Go tool arsenal is pprof. The default profile types are CPU, which measures CPU time, including syscall time. Memory, which gives us a heap dump for both current and cumulative memory allocations. The allocs profile provides us the cumulative allocation, whereas the heap profile provides the current allocation. That is allocated but not yet released by the most recent GC. So adding a custom profile allows us to profile custom execution stacks, for example, when it comes to leaked resources that aren't closed or released. Adding custom execution to a library helps generate a profile which can point to specific problems with the benefit of pprof integration. Let's now add yet another profile to the predefined ones. I'll be giving an idea of how the functions work. Our first dive into the source code. We first create a new profile, custom, and it's here that we add to the predefined types we just discussed. Creating a new profile adds a unique value to the profiles in the profiles map. Now, let's add to this newly created profile. Adding to a profile basically involves adding the current execution stack to this profile, and it uses the commonly known callers function, which fills the slice with program counters of function invocations on this goroutine stack. Now to confirm whether this has been added to the profiles map, we hit the endpoint and there we go. You see it highlighted in red. Now that the action we wanted to instrument is complete, we want to remove this stack from the profiles map, and we do so using remove, which is a simple delete from the map. And as many of you all may know, importing net HTTP pprof is a commonly known prerequisite for using it. And this is for the simple reason that this init function in the package hosts some common handlers, among them the debug pprof ones, which are the most commonly used ones. Now let's talk about the two most common categories of profilers after talking about profiles. We have instrumented profilers, which, as the name suggests, require code to be instrumented. That is, code is inserted at the beginning and end of routines to track the duration. And this instrumentation can be done at various levels, and these are further divided into source code modifying and binary level profilers. So the first modify the source code directly, and the second modify the executables code once it's in memory. Sampling profiler. So these require no modifications the way instrumented profilers do, and these work when the OS interrupts the CPU at fixed intervals and record the execution stack at that point. It then aggregates this result to show the frequency at which the frequency with which certain sections of the code were executed, and it also causes significantly lesser overhead compared to instrumentation profilers. The pprof most of us are familiar with is net HTTP pprof, which is a wrapper around the runtime pprof, which is what we will be focusing on. And this has a CPU profiler, which is an events-based or sampling profiler, where periodically, every 100th of a second by default, a SIGPROF signal is sent, and the Go routine receiving and handling the signal records a stack trace without affecting the rest of the program. We'll be looking into this in more detail in the next few slides. So coming to the internals, this represents the overall flow for the CPU profile. And overall, it's a pretty elegant process which touches upon a lot of packages and parts of the runtime, of which I have highlighted a few here. It looks like a tangle of arrows right now, and in this talk, I will attempt to untangle all of it. So the Go docs define a profile as a collection of stack traces, and simplifying it a great deal, a pprof profile could be distilled into a collection of symbols that could be function names, for example, and their frequency, which can be derived from the stack traces. CPU profiler, let's look at the overview. So understanding the profiler can be divided into two parts broadly. One is the process or workflow of creating and building a profile, and the second is getting the data required to build out the profile. So the key idea here is that there are periodic interrupts by OS timers, and each interrupt, a traceback is obtained and written to a common buffer. And a separate writer routine periodically scrapes from this and builds out a profile. So now let's start. Profiling is started via start CPU profile, and the rate or frequency of profiling is set using a runtime function, set CPU profile rate. And it's chosen to be 100 Hertz by default, since this frequency offers the right trade-off between being frequent enough for effective sampling and infrequent enough considering the cost of getting a profile. So when enabling profiling, it creates a new buffer, CPU prof.log, with a header, and when disabling, it closes the buffer and sets it to false. So CPU prof on here is used to check if profiling is enabled. And now we come to the brass tacks of setting the profiling rate. We first get the current Go routine, which I'll now refer to as G, and disable profiling. And this can be broadly divided into two parts, setting the process profiler rate and setting the thread profiler rate. So SIG action is a system call that changes the action to be taken on receipt of a signal as quoted in the man page. SA handler is the action to be taken for that specific signal. And for the process, we first get the SIG action specifically for signal type SIGPROF. And SIGDFL is the default signal handler which runs when the user hasn't specified a signal handler. And here, if such is the case, we want to ignore any stray SIGPROF signals, and hence it's set to SIGIGNORE, SIGIGN. And after this, setSig is the function which sets the signal action handler using the program counter of the Go default signal handler. Now let's take a look at the Go signal handler. It gets the current Go routine G executing the signal handler and its corresponding OS thread, which I will now refer to as M. It deals with quite a few signals, but the one we are concerned with is only SIGPROF. For this talk, I will focus on the traceback of the Go profile only, not the CGO traceback. And the heart of the Go stack trace implementation is in gen traceback, which is called on panics, and it's called by runtime caller functions, etc., which populates the stack with function related data such as caller info, arguments, number and file, location, etc. So again, here I'll stick to the happy path. That is the case where we have a completely normal traceback on the expected lines. And this stack trace along with a header and a pointer is then added to the profile and the profile begins. Now once the signal handler is enabled, we need interval timers, and here we see iTimer val being used as an interval timer. So here the value decrements after each interval till on reaching 0, it generates a signal, pprof of course, and resets to the interval. So here again, the interval is set in microseconds based on the frequency we first encountered, hertz, headset. Interval timers are divided into types, and here we use iTimer prof and no prizes for guessing which signal it delivers upon expiration. So we set it to these values, and a quick note about iTimer prof, it measures the time during which the process is executing, including syscall execution time. That is the virtual time of a process, the time spent actually executing and not waiting. So this finally brings us to the end of setting the profiling rate for processes. Now only if profiling is meant to be enabled do we venture into setting the thread profiling rate, part 2 of setting the profiling rate. First, we get M, the existing OS thread, and any existing timers are deleted. And again, interval timers are populated with intervals and values based on the frequency. Now coming back to signals, sig event is used for notifications based on certain signals from asynchronous routines. And the notify field denotes the method for notification, and sig number denotes the signal number. Since the notify field has sigf thread ID, the targeted thread will be this specific thread specified in the notify thread ID field. And once the timer expires, again, a sigprof is sent and it's targeted on this thread. So this unique interval timer is created using timer create as opposed to set iTimer as earlier. And this measures the CPU time of the calling thread. And we arm it using set timer set time. And if this does not work, the fallback is the process level interval timer we set earlier. Now, since this profiling rate should be visible to other OS threads as well, we set the profiler hertz field of shed. So shed basically stores a bunch of scheduling related information. And when a G is scheduled to run on an M, if profiling is enabled and if the profiler rate is different on the M compared to the current rate as seen in shed, then the thread profiler is set on this OS thread M. Now coming to writing the profile. So profile builder is used to add a profile from the profile samples that come in from the runtime. And to collect these runtime generated profiles, we have a separate function in a separate Go routine, profile writer, and every 100 milliseconds it reads the profile from CPU prof. And the interesting thing about read profile is that it's a more declaration here in runtime pprof, and it's actually a runtime defined function. So let's investigate this. Look at this directive just above read profile. It's a link name directive, and a link name directive points to a method implementation in the runtime package. Basically an unexported method from the runtime. So this could be best described as a hacky fix or a workaround which lets a function access runtime internals, but it pretends it's a pprof function. So this profile is then added to the profile builder till an EOF is encountered. And then the profile is built, meaning a compressed version of the profile is constructed, a gzip compressed version. And it's written to the writer in profile builder. Now to stop profiling, we head to the stop profiling CPU function where, as discussed earlier, the profiling rate is set to 0 and it's flagged to false. So if profiling is disabled, we set it to a blank interval timer with interval 0, which indicates that it has to be stopped. And the signal handler is also switched back to the one we used before profiling was enabled. So now that we've had an overview of the higher level process of sending signals and acting on them to build out a profile, this completes the first half of the overview. And the second half is about looking into how the data to build a profile is extracted. So I'll introduce a few related concepts which I think are necessary to understand how these symbols are obtained. And as I proceed, you will understand how these fit into the overall picture of things. So since profiling is heavily dependent on symbols, let's understand a bit about symbolization in Go. The previous part was about the overall flow from firing a command or hitting an endpoint to generating and displaying a profile. This section is about how we get the symbols needed to build those profiles. So it's the linker's job to gather the symbols and organize metadata related to them, such as symbol tables, etc., when it's creating an executable binary. So the binary is either in the ELF format, executable in linkable format on Linux, or Maco on Mac OS. And since packages are compiled separately, the modules in a package that are not local to the package or not defined in it are not handled by the compiler. Since it has no idea where these are, it's the linker's job to deal with them. So the linker gathers symbols from all referenced packages and loads them into a binary image and calculates an address relative to this image. This is in contrast to the earlier addresses that were relative to the specific object file. So as you can see, a linker has a narrower, a broader view than what the compiler has. And the linker then relocates these symbols in, and the process is called relocation by the linker. So let's look at the stack of a simple Go routine. Starting from the RIP, the register pointing to the current instruction, and calculating the program counters of the, collecting the program counters of the callers of this function is called unwinding. Frame pointer unwinding is the process of following the base pointer to the first frame pointer and so on, and collecting the program counters just above frame pointers. And runtime.callers, which I mentioned at the very beginning, is a commonly used function that gives us the return PCs on this Go routine stack. And pushing a frame pointer on the stack for a function called does have an overhead in terms of performance, but that could be considered a bargain due to the increased compatibility and therefore insights with third-party debugging tools. So converting the memory addresses in these stack traces to human readable symbols is called symbolization. The executable files have multiple sections, and we are just focusing on one. That is the Go PCLN tab or the Go PC line table. This is unique to Go. And this has a line table mapping program counters to locations in the source code. And now that we've spoken about the stack, let's talk traces. So let's go to the gen traceback function, again, which we have looked into earlier, and look at it. We first get the value of the current program counter and stack pointer and populate the frame with them. We then have find function, which returns the function metadata for that program counter. And the way it does it is pretty interesting. So it initially gets the module data for it. And now what's module data? So the first module data is usually the module containing the runtime. And then on, all the other modules are organized as a linked list, and they are in the order that they are loaded by the linker. So now we touch upon the linker. And it has a field, one among many, text sect map, which is a slice of text sects, each with a base address and a section address that can be calculated. And to find the function mapped to that program counter, there is a rather nifty way of doing it by bucketing function data and then further dividing it into sub-buckets based on the program counter alone. So now that we have the offset, let's find the bucket and the sub-bucket. And the first step after finding the bucket is finding the bucket position by multiplying the bucket index with the size of the bucket. and adding the index of the function and the sub-buckets brings us to the function sub-bucket. So starting from the sub-bucket, we increment the index till we come to the program counter offset of the function, and the function of offset field from the function table, another PC line table, at that index is the function offset. So this metadata, the one we just got, contains a PCSP offset into the table. Now a PCSP maps program counters to SP delta, stack pointer deltas, like you can see in the diagram. And function SP delta does a linear search till it finds the closest PC SP delta pair. And it then adds this to the stack pointer to get the frame pointer. Since the distance between a program counter up to but not including the next program counter is a part of this table, you can see why there isn't a requirement for physical frame pointers in Go, unlike in frame pointer unwinding. So earlier I had mentioned the cost of unwinding and passing when discussing the rate of profiling. It you can consider the complexity of Go PC ln tab unwinding as linear, which is similar to frame pointer unwinding, but the constant overheads for Go PC ln tab are higher. And so that way I can say that this debate between frame pointer unwinding versus using Go PC ln tab is not a very cut and dry one. And to sum up, assuming a 1 microsecond overhead per stack trace unwinding is a good approximation, but for the built-in tracer, it could be significantly higher. So back to this diagram, we have worked our way through this, starting from the handlers on top to the interactions with the runtime pprof, when setting profiler timers, and then some understanding of the process of extracting the symbols and gathering the profile samples to a common buffer. So there's a lot more to the internals of profiling, but I hope this short talk piqued your interest while giving you a modicum of understanding about the whole process. Thank you.